Okay, in this section we're going to talk about concavity and curve sketching. Here we see a picture of f of x equals x cubed. Notice that it is concave down between negative infinity and 0, and it's concave up between 0 and infinity. The concave down just means that it's open downward. Concave up means that it's open upward. Notice the f primes, the slopes, between negative infinity and 0. As you get closer and closer to 0, your f prime is decreasing. Now remember, f prime is the slope of that tangent line, so the tangent lines are getting smaller and smaller. As you move from 0 towards infinity, you'll notice that your tangent lines are getting steeper and steeper, so your f prime, your slope of those tangent lines, are increasing. Now the graph of a differentiable function y equals f of x is concave up on an open interval I if f prime is increasing on I, and concave down on an open interval I if f prime is decreasing on I. In order for our f prime to be increasing and our f prime to be decreasing, we will look at the second derivative. The second derivative is the slope of the first derivative. And where it's increasing, it has a positive slope, and where it's decreasing, it has a negative slope. So that leads us to the second derivative test for concavity. So let's let y equals f of x be twice differentiable on an interval I. If f double prime is greater than 0 on I, then the graph of f over I is concave up. If f double prime is less than 0 on I, the graph of f over I is concave down. So we can determine where a graph is concave up and concave down by looking at its second derivative. Here we have the graph of f of x equals x squared. Notice that it's concave up on every interval. If we take the second derivative of this function, the first derivative of x squared is 2x. The second derivative, the derivative of 2x, is 2. Now notice that that is a positive number, and it would be positive everywhere. So since the second derivative is positive over the entire interval of numbers from negative infinity to positive infinity, this graph is concave up from negative infinity to positive infinity. Now let's look at this graph. We have here the graph of y equals 3 plus sine x. And then we have the graph of the second derivative, which is negative sine x. Remember, if we take the first derivative of 3 plus sine x, the derivative of 3 is 0, and the derivative of sine x is cosine x. When we take the second derivative, the derivative of cosine x is negative sine x. So this is where the second derivative comes from. Now we said that where the second derivative was negative, so the second derivative is negative here from 0 to pi, then our graph of our function will be concave down. Where our second derivative is positive, which here is from pi to 2 pi, our graph is concave upward. Notice here at pi is where this changes. Sorry about that. It's where this changes from being concave down to being concave up. We call that point there at pi an inflection point, or a point of inflection. That is where our graph changes from being concave down to concave up, or concave up to concave down. So a point where the graph of a function has a tangent line and where the concavity changes is a point of inflection, or an inflection point. Now here we have the graph of y equals x to the fourth. And we want to look at what its inflection points would be. Well, the inflection point is going to be found where the second derivative is 0, because that's where it's going to change from being negative, second derivative being negative, to the second derivative being positive, or vice versa, from the second derivative being positive to the second derivative being negative. So if we take y equals x to the fourth, then its first derivative is 4 times x to the 4 minus 1, which is 3, so 4x cubed. And then if we take the derivative of 4x cubed, we say 3 times 4 is 12, subtract 1 from 3, we'll have 2. Now 12 is positive, and we have x squared. And remember, x squared will always be positive whether we plug in a negative number or a positive number. The only exception to that is if it were 0, and of course if it were 0 it would be equal to 0. So if we want to know where the second derivative is equal to 0, 12x squared equals 0. We could divide by 12, which gives us x squared equals 0. Take the square root of both sides, and x equals 0. Now x equals 0 is a possible inflection point. However, notice that it does not change from going being concave up to being concave down there. Even though the second derivative is 0, it does not necessarily have to change concavity at that inflection point. So like critical points, we looked at critical points, and it did not necessarily have to change from increasing to decreasing at a critical point. It's the same thing with inflection points. It does not necessarily have to change concavity there. If we think about the second derivative, no matter what value we plug in, whether it be a negative value or a positive value here, it's going to be a positive second derivative, which means it's always going to be concave up. Now we can also have a point of inflection where y double prime does not exist. So if we take this graph, which is y equals x to the 1/3, and we think about the second derivative. Well, the first derivative would be 1/3 x to the 1/3 minus 1, which is negative 2/3. And then to take the second derivative, that would be negative 2/3 times positive 1/3 is negative 2/9. Subtract 1 from 2/3 and we'll have negative 5/3. Now thinking about what this looks like, that's negative 2 in the numerator divided by 9x to the positive 5/3 in the denominator. Now this is never equal to 0. However, it is undefined for x equals 0. Okay, so it's undefined at x equals 0. So that's another place that we can change concavity. You'll notice here that this graph is concave up all the way up to 0, and then it's concave down to the right of 0. So from negative infinity to 0, it's concave up, and from 0 to infinity, it's concave down. So we can have a point of inflection either where y double prime is 0, or where y double prime does not exist. Now let's do one more example here. Let's look at a position function. We have a particle moving along a horizontal line with position function s of t equals 2t cubed minus 14t squared plus 22t minus 5, and t must be greater than or equal to 0. Find the velocity and acceleration and describe the motion of the particle. Okay, so remember that the velocity is the first derivative of the position function. So the derivative of 2t to the third would be 3 times 2 is 6, t squared. 2 times 14 is 28, so that's minus 28t. And then the derivative of 22t is 22, and the derivative of 5 is 0. So that is our first derivative. Well, if we want to think about the motion of this particle, let's think about where the velocity is 0, because that's where our particle is going to stop. First, I'm going to factor out a 2. That would be 2 times 3 squared, 2 times negative 14t, and 2 times 11. And we know that 3t times t gives us 3t squared, and we'll either have to have 1 times 11 or 11 times 1. Now we want this in the middle to be negative 14t. So if I put a minus there, that will give us negative 3t in the middle, and a minus there, that'll give us negative 11t in the middle, which adds together to be negative 14t. Now we're thinking about where this is equal to 0. Now remember that 2 is never going to be 0. The only way that this velocity can be 0 is if either 3t minus 11 equals 0, or if t minus 1 equals 0. Well, here we'll add 11 to both sides, which gives us 3t equals 11, and divide by 3, and we'll have 11/3. And think about 11/3, that's 3 2/3. Add 1 here, that's t equals 1. So if we think about our velocity, this is going to stop when t is 1, and it's also going to stop again when t is 11/3. Now let's think about the acceleration. The acceleration, of course this was the velocity. The acceleration is the derivative of the velocity function. So if we come back up here and look at our velocity function, 2 times 6 is 12. 2 minus 1 is t to the first power. The derivative of negative 28t is negative 28, and the derivative of 22 is 22. Now we can also see where our acceleration is 0. If I add 28 to both sides, I'll have 12t equals 28. Divide by 12, I'll have 28 over 12. And 4 goes into the top 7 times and the bottom 3 times. So the acceleration is 0 at time t equals 7/3, which is 2 1/3. Now if we plug in to those functions, you'll see that between 0 and 1 second, we said it stopped at 1 second, you have a positive velocity, which means it's increasing and moving in the positive direction or to the right. Between 1 and 11/3, you have negative velocities, which means decreasing or moving to the left. And then for the values greater than 11/3, your velocity is positive, so it's increasing or moving to the right.